by various prizes. PK's prize from 2010 and the highly prestigious prize of the Alan Waterman, right? Prize from 2012, and he's well known for the very exciting and provocative talks that he likes to give. So I'll give the stage to him.
All right. So, well, thank you so much, Dorit. That was very kind, and it is always a pleasure to be here at Hebrew University. In fact, I have to think about making sure that I don't give the same talk that I gave here the last year, because I come here so often. But so as Dorit said, a lot of my work is about quantum computing. By the way, I'm just recovering from a cold, so if you can't hear me, that's let me know. I'll try to speak up, but that's why my voice sounds weird. Okay, but this talk will not be about quantum computing or about computational complexity. It will touch on them, here and there, maybe incidentally. But this talk will sort of go back to earlier in the history of computer science, to the concept of computational universality itself, and to the two fine people who you see here, Ada Lovelace and Alan Turing. Of course, this is the Ada Lovelace Bicentenary lecture. So I thought, so given that, and also given that this is a mixed audience, as I understand, with computer scientists, philosophers, physicists, and so forth, I thought, and given that over the last few years, my students and I have actually been thinking about some, very, very elementary types of questions related to computational universality. I thought that would be a fun thing to talk about. Okay, so there are two different things that people mean by universality in the computer science context. The first one is the existence of a universal machine. Okay, or I like to call this the existence of the software industry lemma, right? That basically says once you've got a powerful enough programming language like Turing machines, there is going to be, a single machine that can just simulate any other machine which is described to it as part of the input. Okay, so there is a universal machine. Okay, now the second notion of universality is that is, I guess, the Church-Turing thesis, that which says that there is some universality class for computation. Okay, there is a ceiling of expressive power, and you sort of very quickly reach that ceiling, and then adding more functionality into your computer or your programming think so it doesn't take you any further than that. Okay, and I like to explain this by reference to, I think that sometimes, like when I teach my undergraduates, I struggle to explain why is this not completely obvious, right? Because in the modern world, we sort of deal with computation and with simulating one thing with another thing, so frequently that it's sort of hard to remember, why this was something that had to be discovered. Okay, but I can at least say for myself that when I first learned, as a kid, what programming was. First of all, it was a revelation. I like to say it was at least as big for me as learning where babies come from, right? This is where video games come from, right? And I was just you asked me to provoke. All right, good. But I was like, why is no one, and there was the same feeling of like, why is no one told me about this earlier, right? But then, the first thought was okay, so, I learned some, Apple Basic or GW Basic, and then I was sort of became vaguely aware that there are programming languages that more serious people use, and so it seemed obvious that people use those more serious languages because they let you do things that you could not do in GW Basic, right? And so, okay, they must let you do even more. And then, and then my dream in life became to, invent a programming language that would let you do even more than those languages, right? And, it seems there could be an infinite hierarchy of more and more powerful programming languages. Okay, so learning the Church-Turing thesis actually was somewhat of a second revelation for me, right? In principle, GW Basic can already say everything that all these other languages can say, it may, be a terrible choice practically, but it's, okay. So in this talk, I'm going to be focusing on this second notion of universality, this sort of ceiling of expressive power notion in a few different contexts. And once we know what to look for, we sort of see these expressiveness ceilings all over the place in computer science. So this is the sort of basic case that, just about any programming language, as long as it's complicated enough, there are languages that are not universal, that whatever, they only have straight line programs or only have loops of with a bounded number of iterations. But any expressive enough language is going to be equivalent to Turing machines. Okay, likewise, in the setting of circuits, almost any Boolean logic gate that you could make up, is going to be a universal gate. One that if you compose enough of them, you can express any Boolean function. And the same thing is true in the setting of quantum computing. Almost any quantum gate, so almost any unitary transformation that you could think to invent on, let's say, as few as two quantum bits, 2 qubits, will have the property of universality, which means that by composing enough of that unitary transformation on different pairs of your qubits, in some order, you can implement any transformation on any number of qubits to any desired precision. Okay.
What do you mean by almost any?
So this is true both in the mathematical sense, that if you pick one at random under the Haar measure, then with probability 1, it will have this, 100% of them will have this property. Right, and it is also true in the intuitive sense that almost any that we could make up, will have this property. Okay, there are a few very interesting ones that are not universal, which I can come back to later.
Whereas almost in the previous sentence means non-trivial.
So here, you could say almost means that as n gets large, the fraction of them approaches 1.
This is asymptotically almost.
Oh, I see.
Yes.
So it is.
Okay. Yeah. I thank you for. Okay.
We go with high probability.
Yeah. Okay. So so these are all very, very well known phenomena, and you might wonder what could there possibly be to say about them that's new. Okay, well, the way that I like to think about it is, so universality is so, well understood today, and it's so common, right, that, it almost presents a problem, okay, which is that, if almost any laws of physics that you could think to invent are going to be universal in the sense of, able to simulate a Turing machine or able to compute any Boolean function or whatever, well then what is special about our laws of physics, right? So this, here I've shown Conway's game of life, which is a very famous cellular automaton, right, where each cell is, either black or white at each time step, and at the next time step, it will decide whether to be black or white by summing up the the 8 neighboring cells and and making a decision based on that, right? There's some simple rule for it. Okay, and so Conway's game of life was invented in 1970, and this was a very famous example where you just take this incredibly simple local update rule, on a 2-dimensional grid, and you iterate it over and over again, and you get, what looks almost like physics. So it looks like this, incredibly, complicated, emergent behavior. You could even point to features of this world, and argue that they're analogous to our world, right? So this world has a speed of light, right? It's, a signal can only propagate at the speed of the update rule. It has a grain, which you could say is analogous to the Planck scale. It has some symmetries. Well, in this case, there's like a discrete, fourfold symmetry and translational symmetry. So certainly much less symmetry than our laws of physics have. But is that really the difference? I don't know, right? So it was discovered early on that you can, within this game of life, you can build a universal computer. So you can build a circuit that will evaluate any Boolean function. You can even build a Turing machine that will run for, an unlimited amount of time, and that will, let's say, erase the entire board, make everything zero if the machine halts, and otherwise not do that. Okay, so all the computations that can be done in this universe, this was my representation of our laws of physics, whatever the standard model, can also be done in this universe. Okay, and then you could say, what are really the differences? And so this is a question I've been curious about for a while, and so I've been very curious to explore what are sort of more fine-grained notions of universality. So what are, if you have a bunch of laws that are sort of all computationally universal, what are more fine-grained distinctions that you can make among them? Okay, and so I want to, in this talk, give you, some various concrete examples, I guess, of what kind of, technical questions, asking that can lead you to. Okay, and so actually, most of this talk will be work by my students. There's one nice thing about this area is that there are a lot of really accessible open problems, and I can give them to students and they answer them. And so I'll be able to show you a few examples of that. So I'm going to tell you about my student Luke Schaeffer constructed the first example of what's called a physically universal cellular automaton. Okay, which is an automaton which is sort of universal in a much stronger sense than Conway's game of life is universal. Okay, and this work actually won the Best Student Paper Award at ICALP, which was held like about a year ago at the Weizmann Institute. Okay, so yeah, and then I'll tell you about work I've been doing with Adam Yedidia to construct to see how small of a Turing machine can you construct that sort of encodes really mathematically interesting behavior, and I'll try to explain why someone might care about that question, and then I'll talk about recent joint work with my students Daniel Greer and again Luke Schaeffer, which gives a complete classification of all the classical reversible Boolean logic gates. So gates that never destroy information, giving a complete characterization of which of those are universal and which are not universal, and in exactly which senses. Okay, and along the way, I'll tell you some of my favorite open problems in this broad area. Okay, So let me start by talking about this notion of physical universality. Okay, so the starting observation here is that you may have a device which is capable of doing universal computation, but that still doesn't mean that it is able to manipulate the physical world in any way that you would like. There were, in fact, there was a paper, there were a whole bunch of articles by people named Wegner and Golden, over the last couple decades that were arguing that the Church-Turing thesis is wrong. Okay, and why is it wrong? Well, they say that it's wrong because Turing machines are not interactive. Okay, Turing machines, they just do they just take an input and do something with it, and they don't interact with the user, and they're not networked, they're not on the internet, and and therefore, there are devices that do things a Turing machine cannot, and this falsifies the Church-Turing thesis. Okay, so people ask me about, as tends to happen, they started emailing me about this, and I had to write something on my blog about it. So I sort of parodied it by saying, well, look, it is also the case that, a Turing machine cannot toast bread. Okay, and so we could imagine a new device with a toaster-enhanced Turing machine, right? And when we say that this also falsifies the Church-Turing thesis, because this is also doing something that a Turing machine cannot, right? Okay, of course, this, we're just talking about, a question which is not the question that Church and Turing were claiming to answer. Okay, the question they were claiming to answer was about, what do you need to simulate the internal logic of any given machine? So in the case of a toaster, what do you need to do to, in order to decide how brown the bread should be or something, right? A Turing machine can decide that for you, hopefully, unless you have a very weird kind of toaster. Okay, but then if you wanted to actually toast the bread, well, of course you have to hook your computer up to an appropriate peripheral to, make it do the thing that you want in the physical world. Okay, but, I want to take this, instead of just making fun of them, I want to take this a little bit seriously, right, and say that actually, there are interesting questions about, devices, that may be computationally universal, but that might not be able to, implement, whatever kind of robotic behavior you want, to manipulate the physical world in whatever way that you want. Yeah.
Isn't it just a question of what is the scope of your machine? If you define your machine to be the collection of the subsystems, then you're fine? Or is there a difference?
There's so I'm not sure. So you can always say, well, my machine is so that, like, in quantum computing we have a notion of encoded universality, right? And you can say my machine is universal within this subspace, right? So like there's this philosophers have this famous example that they use a lot, that if you do a computer simulation of a thunderstorm, it doesn't make anyone wet. Right, and then someone else could respond, well, a simulated person in the simulation would get wet, right? But this is the issue, right? That you may want to not only do a simulation of something, you may have some actual base physical world that you care about, in which you want to affect some desired transformation. Okay, so there's a whole very fun set of questions that I hang out with some of these Singularity or AI people, and they talk a lot about this kind of question. Suppose that I gave you as much pure computational power as you want. So I gave you an oracle for NP-complete problems, or we could even say for the halting problem. Right, then what could you do with that, in the physical world? Could you use it to conquer the world, right? Explain to me how, right? What's the, you could break all the public key cryptography, you could mine a lot of bitcoins, but after that, what's the next step in your plan for world domination, right? How do you leverage computational power into real temporal power? Okay, it's a very fun thing to think about, right? How would you cure cancer, right? How would you build a rocket to get to the next star? How would you manipulate the social world? Make people do what you want, right? So you could almost define a nerd as someone who is frustrated about this, right? Someone who has all this computational power, but they're just unable to convert it into the sort of manipulations of the physical world that they want. Okay, so I guess to be more formal about it, Dominic Janzing, who's actually mostly a quantum computing person, he wrote a paper in 2010 where he raised, a beautiful question, which I hadn't seen before. He said, let's call a cellular automaton physically universal if it has the following property, that, if you take any sub-region of the automaton, so let's say any square grid of any size, right, and now I take any mapping, of states of that, within that region to other states within that region, okay, then I can affect that mapping by appropriately initializing the complement of that region. Okay, so he's saying, I can build a, for like let's say, what I want is to count the number of atoms, that are in a box, and if there's a prime number of atoms, then I want there to be a next a hamster in the box. Okay, and if there's a composite number of atoms, then there should be an alligator. Okay, then I ought to be able to set up a machine outside of the box, such that when I leave the machine to run, that this is going to be the behavior. Okay, so if there's this property, then we'll call the automaton physically universal. Okay, so this certainly, yeah.
Isn't that too strong requirement that you can do this on any region and inside the automaton?
Any finite region.
But shouldn't you just be able, like you said, select the sandbox and say, I'll just work on this sandbox? Why do?
Well, yeah. So we pick a sandbox, okay. but the point is that the sandbox can have any size.
Okay.
Okay, it can be as large as you want. Okay, so so certainly this implies computational universality, at least in the circuit sense. Right, because one of the things you could do in the sandbox would be to evaluate a Boolean circuit there. Right. Interestingly, it does not imply universality in the Turing machine sense. Okay, because a Turing machine might require an infinitely large sandbox. Okay, but on the other hand, this is a much stronger notion than circuit universality. Right, because this is saying I can do any manipulation that I want of the physical states. And so he asked, does there exist a cellular automaton with this property?
Has to keep the physical laws of the world or something also?
Yeah. The machine that you build, and the sandbox, they're all going to be obeying the laws of this automaton, whatever they are. Those laws are never. Yeah, right. Those laws can never be violated. Yeah. I'm sorry. The laws here. The laws are the laws of the automaton. Yeah.
So this is specifically two-dimensional grid, or?
Let's say for now that it's a two-dimensional grid. Okay, we can change that later if we want. But yeah, let's say two-dimensional. Okay, so you can.
How about a one-dimensional grid?
Yeah, another good question. Okay, I'll come back to that. All right. So, but if we can't even do it in 2 dimensions, then it would be all the harder to do it in 1, right? Okay, so let's look at some examples. Conway's game of life is not physically universal. The reason is simply that it's not reversible. Okay, so imagine that in the middle of my sandbox I have a single isolated 1 cell, right? Then the rules of the game of life imply that 1 cell will just immediately disappear at the next time step. And so then, no matter how many complicated detectors I set up outside of the sandbox, I'm never going to know whether there was that little particle there in the middle or not. There's no way I can know that. Okay, so forget it, right? So at the very least, in order to be physically universal, my cellular automaton had better be reversible. Okay, better preserve information. Okay, but then even among reversible cellular automata, there are many that are not, that can be seen to be not physically universal. And this is often because they allow the construction of impenetrable walls. Okay, so let's say that this purple square, this is my sandbox, right? But now suppose that, using the rules of my automaton, I can construct some walls that are just never going to go away, right? They're just going to stay there forever, right? Then it doesn't matter what I set up, outside of this purple square. Okay, I would never be able to find out what is inside of this blue rectangle, right?
Presumably this was written in GW Basic, huh?
Yes. I'm sorry. This was written in a different Microsoft product, PowerPoint. Yeah. So my programming ability sort of went from GW Basic to Q Basic, to C and C++. They went up that hierarchy, and since then they've slid downward until now I only remember how to make PowerPoint animations. Okay. So all right. So now I will. I like this problem. So I gave it to Luke Schaeffer, and so he managed to construct the first example of a cellular automaton, which is proven to be physically universal. Okay, and the rules of his automaton are extremely simple. So the automaton just consists of a bunch of particles that move diagonally across the grid. Right, like at 45-degree angles at a unit speed. Okay, so each particle, each one, these little arrows, they just move, in one of these 4 diagonal directions. Okay, and and usually they just pass right through each other. Okay, so 2 could hit each other and they'll just keep going. 4 could hit each other and they'll keep going. The only time anything non-trivial happens is if 3 arrows converge at one point. Okay, like here. Okay, and in that case, what happens is that the one that hits at a right angle to the other 2 gets reflected. All right, so that's the whole automaton. And so now notice that this automaton certainly has the property that you will not be able to construct impenetrable walls with it. Okay, in fact, you can prove a theorem that says that no matter how you start the arrows, within a very small amount of time, they're just going to evolve into 4 clouds of arrows that are flying away. So you sort of cannot keep anything confined, for too long here. And that is important because, Luke actually wants that, okay? Because he wants that whatever was the initial state inside of this sandbox, you'll be able to read it using machinery which is outside of the sandbox. Okay, and so now, the basic idea of his construction, you start with the initial state, which is some subset of arrows that are inside the sandbox. Those arrows are all going to fly out, and notice that this is a reversible cellular automaton. So if you would now examine these 4 clouds of arrows, and which arrows are missing here, that will encode all of the information about what was the initial state. Okay, so now all we need to do is intercept these arrows with like an array of interceptors, and then get that into like a linear array of bits that encodes the initial state inside the sandbox. Then get that state into a Turing machine or into a circuit that will do any computation on it that we want. Then take the outcome of that computation, rearrange it back into arrows, which will now converge back onto the square. Okay, and so that at a single moment in time, but which we can tell you exactly what that moment will be. That in the square will be, the new, the hamster or the alligator, right? Whatever new thing you wanted. All right. So,
but you didn't assume that the transformation has to be computable, did you?
Well, it's a transformation. It's a finite transformation. Okay, it's a mapping from a finite set to a finite set. So you could just give an explicit description of it. So certainly it will be computable for that reason. It might require a circuit which has size exponential in the size of the sandbox. That's unavoidable. But okay, so here's just a little nice picture of just one little piece of the construction, where you're sort of intercepting these arrows and getting everything into a long line of bits, which you then do computation on. Okay, so if you go to his webpage, he has a lot more of these pictures, right? Which is a nice thing about this subject, that it lends itself to nice pictures. Yeah. So okay. So I should say, yeah. By the way, to answer Noam's question, since then there was a group of authors in Finland, I think, who managed to improve on Luke's construction and give a one-dimensional, physically universal cellular automaton. Luke also managed to generalize this to give a two-dimensional, physically universal quantum cellular automaton. Okay. Yes.
After you read the bits of the clouds, can you also in this model actually compute a Turing universally compute transformation you want?
Okay, that's an excellent question. The answer is this model actually is not universal in the Turing machine sense. Okay, and there's a very interesting reason for that. The reason is that, if I start with any finite number of arrows, then after a finite number of steps, they're just, as I told you before, they're just going to be 4 clouds that are flying off to infinity, right? So I can't get like an unbounded amount of computation from a bounded initial state. Okay, I can only hope in this model for universality in the circuit sense. Okay, so this is also a model that, this is also something that shows that physical universality does not imply Turing machine universality. Okay, so I can't resist telling you my favorite open problem about physical universality. So this will be a quantum computing question, so this is a question that Greg Cooperberg and I asked around 2006 in a paper. But since then, we worked on it, we couldn't answer it. But since then, the same question has been cropping up again and again in different contexts, including contexts related to the black hole information problem and quantum money, other things. So all right. So let me tell you the question. Okay, the question is, for every unitary transformation, for every quantum mechanical transformation that you could do on n qubits, is it the case that there is some classical Boolean function, some classical oracle f, if you like, which would allow you to realize the unitary transformation u in polynomial time if you had oracle access to f? Okay. So I'm asking, for every unitary transformation, is there some classical computational capability that I could give to you that would allow you to apply that unitary efficiently? Okay. So again, I'm giving, I'm letting you be, as good of a nerd as you want. Okay. I'm giving you as much computational capability as you could ask for. F could even encode some uncomputable problem, something exponentially hard, whatever. But then the question is, how do you use a quantum oracle? You can query F in superposition over many basis states. Now, how do you use that to implement the desired unitary transformation? Okay, can this be done for every unitary? Okay, my conjecture would be that the answer is no. I can, so there's no obstruction to this based on a counting argument or anything, right? It's true that there's doubly exponentially many unitaries on n qubits, but there, you can also have doubly exponentially many oracles, right? So there's no counting obstruction. The obstruction will have to come from some other source, but still, it seems unlikely to me that you could do this.
You have a candidate Q?
A Haar random one. I don't know, or we could take, for example, the measurements that you would have to make in the hidden subgroup problem. Those might be another candidate, right? Or that's a good example where we know what unitary we want, but but not only do we not know how to implement that unitary efficiently, even if p were equal to p space, we still wouldn't know how to implement it efficiently, right? And that's the part that really interests me. Okay. So just to compare, it is pretty easy to show that for any quantum state of n qubits, there is some oracle function f, that would let you prepare the state efficiently. Okay, so all this function f has to do is just sort of encode, like a binary search strategy for preparing the state. So it has to say, here's how you should prepare the first qubit, into what superposition of 0 and 1. Okay, and then conditional on the first qubit being 0, here is how you should prepare the second qubit. And conditional on it being 1, here's how you should prepare the second qubit. And then, conditional on the first 2 qubits, here's how you should prepare the third qubit, and so forth. Okay, so as long as the oracle gives you all of that information, and you have quantum access to that oracle, then you could prepare, any desired state psi. Okay, but how do you actually implement any desired transformation of quantum states? I conjecture that there are cases where this can't be done. I think it's a beautiful question.
Excuse me.
Yeah.
F is like a non-uniform. F is like an infinite family of
Yeah. So okay, you can either have an infinite family, or for simplicity we could just fix n, right? Just fix n, and then just say u is n qubits, and and f is any oracle function that that takes inputs that are a polynomial in n number of bits.
Yeah, but if you fix n, you just lost your supposed advantage of being non-computable to whatever degree, right?
Sorry, I don't understand.
Well, you said that f is very powerful because f can be anywhere up the halting hierarchy.
No, I mean in the limit as you increase
right.
n, as a function of n. Right. Yeah. Okay. All right. So the next thing I wanted to tell you about is there's a question we could ask. How weird or improbable or complex or artificial do universal computers have to be? And this is sort of motivated, if you like, by the origin of life debate, right? Where we don't know how the first self-replicating molecules arose, on Earth or possibly on some other planet. Darwinian evolution sort of only deals with what happened after that, in some sense, and there's a view that the first self-replicating molecules could have just arisen by an improbable coincidence, right? Because after all, it only has to happen once. Right, but then the next question we could ask is, well, exactly how improbable are we talking? Okay, and it's clear that this is only a question of constant factors in some sense, right? Because, a self-replicating molecule has some constant size, so it has some constant non-zero probability of just arising by chance. Okay, but this is one constant factor that, despite being a theoretical computer scientist, I think maybe we should care about. Okay, because depending on whether this constant factor was a tenth or 10 to the minus 10,000, this would determine whether a self-replicating molecule would have a good chance of arising within our observable universe, or would have next to no chance of arising, right? And would determine how much extraterrestrial life we should expect there to be, and things of that kind. Okay, so when we translate this into the setting of computability, becomes a question of, we could have lots of different programming formalisms which are all equivalent to each other in the Church-Turing sense. They can all simulate each other. But some of them still might be, much more convenient. This is why we don't all program in assembly language, right? We use better programming languages, right? We use languages where where we have to say less in order to get over the threshold to be doing something interesting. So there could be cellular automata that are technically universal, Conway's Game of Life. But in order to see the universality, you have to construct these enormous and very, very, very finely tuned and very improbable configurations, right? So that, like on a sort of generic life board, you might expect them to never arise. And so then, we could ask, well, is universality sort of more pervasive than that, right? Is it something that we can sort of expect to arise naturally from sort of generic initial conditions, right? So, these are of course vague questions, but there are lots of ways that we could make them more precise. So there was a very, very early pastime in theoretical computer science in the 1950s and 60s was this competition to design the smallest possible universal Turing machine. Okay, so the smallest machine, that with given an appropriate input will simulate any other machine. Okay, and Marvin Minsky, I think, found such a machine, which he found a universal Turing machine with a 4-symbol alphabet and with just 7 states, compared to, I think hundreds of states in Turing's original construction. Okay, and that stood as the record for a long time. Then Stephen Wolfram in 2007 announced a competition. He had a particular machine with 2 states and 3 symbols, which I think was in his book, his revolutionary book. And here's a picture of it. Okay, and he announced a $25,000 award for anyone who proved that this machine was a universal Turing machine. So then there was a 20-year-old student named Alex Smith who claimed the award a few months later, and journalists asked him why, and he said he had nothing better to do that weekend. And I thought this was an excellent motivation to enter this competition. Now Wolfram's sort of main claim in his New Kind of Science book is that this kind of thing, these sort of very, very simple computational models that are already universal, that this vindicates what he calls the principle of computational universality, which basically says that universality is everywhere. It's not something that you have to engineer some sort of special contraption to obtain. It's just the pervasive default case in nature, right? So it's not clear exactly what one means by that. But in any case, I think there's a very specific objection that I would raise against this sort of thing, these small universal Turing machines being taken as evidence for this claim. Okay, and the objection that I would raise is that in these constructions, what inevitably happens is that you trade, a very small universal Turing machine for an enormous and elaborate encoding on the input tape. Okay, so in order to, get this machine to simulate any other machine, you need to take the other machine you're trying to simulate and encode it in a ridiculously elaborate way onto the input tape. Okay, and then, you also, there's a lot of interpretation. There was actually debate about whether Alex Smith had solved the problem, because there was debate about what exactly counts as universality. Okay, because to take some examples, the machine actually never halts. Okay, you looking in from the outside have to realize when the machine, would have halted, right? Okay, fine, but you need an initial state which actually you initialize the entire infinite tape, in a non-periodic way, right? Just in order to get it to get this tiny machine, this one here, I guess to do the thing that you want. Right, and so to me, this is really just, pushing the lump under the rug somewhere else. Right, this is just shifting all the complexity into a different place. Okay, our universal machine is small, but but our input encoding has just picked up all the slack. Okay, so I think in order to really ask the question that that we want to ask, we have to look at, how small of a machine does it take to do some concrete, thing that doesn't require any input encoding, right? Just some fixed task that you could do, like, let's say, with a blank input tape. Okay, and this is a kind of question that people have studied for, people have played at for a while under the name of code golfing. Okay, there's this. I learned this from my students, but apparently there are competitions to write the smallest possible program that does some given behavior, and there are even programming languages which are designed for fun code golfing. So here's one way that we could ask this question. It involves this famous function called the busy beaver function. Okay, so busy beaver of n is the maximum number of steps that a one-tape, two-symbol, n-state Turing machine can possibly take on an initially blank tape and then halt. Okay, so take all the possible n-state Turing machines. Some of them will run forever, on a blank tape. So all of those we just throw away. Okay, and then among the ones that halt, there must be one that runs for a maximum number of steps. So whatever that maximum is, that is the nth busy beaver number. Okay, so here is the what's known about the first few values of this function. People have been playing it, pinning down this this function for the last 50 years or so. Okay, and so the first four values of the function are known. This one is trivial. This one is given as a homework exercise. When I'm feeling sadistic, I guess, for students. This one was a paper. This one was another paper. And they're papers because there's a bunch of machines where you have to prove that they run forever. And these are instances of the halting problem. And busy beaver 5 already is not proven. We have a lower bound on it, and there's some hope, I think, that this could be proven in the foreseeable future. It's down to about 20 machines that no one has proven that they run forever. Okay, with 5 states. But if someone can do that, then busy beaver 5 might be determined. Busy beaver 6, we seem extremely far from knowing, and people debate whether we could ever whether we'll ever know busy beaver 6. Okay, and famously, the busy beaver function grows faster than any computable function. Right, it grows uncomputably quickly. And this is easy to see because if you could compute any upper bound on the busy beaver function, then that would also let you solve the halting problem. Okay, so this is like a sequence of numbers that very concretely encodes the difficulty of the halting problem. And there's a further statement that we can make, which is that because of Gödel's incompleteness theorem, there must be some finite value k, such that busy beaver of k and busy beaver of k plus 1 and so forth are all independent of the axioms of set theory. Okay, anyone see why that is? Well, it's simply because you could build a machine with some finite number of states that just searches through all of the theorems of set theory and that halts if it ever finds a contradiction. Right? Now, presumably that machine runs forever because set theory is consistent. Okay, but in order to prove that machine runs forever, you'd have to prove the consistency of set theory, which of course set theory can't do if it's consistent. Okay, and then if that machine has k states, then set theory also cannot prove the value of the kth busy beaver number, because if it did, then it would prove that particular machine runs forever. Okay, so now the question that we can pose is, well, where exactly does this happen? Where do you cross this threshold into this sort of philosophically crazy behavior? Are we talking about a machine with 10 million states? Okay, because maybe that's not so unsettling then, right? Or are we talking about a machine with 100 states? Or are we even just talking about a machine with 10 states? Okay, and again, I think this is a constant. This is a constant that I actually care about. Okay, I want to know the value of this constant. Right? What is the k such that busy beaver of k is independent of set theory? Okay, and this is sort of like you could say it's a more concrete version of a question that a lot of people have asked over the last century, which is, could there be, Gödel's theorem tells us that there are some questions of arithmetic that are independent of, of our formal systems. But what about Goldbach's conjecture? What about the Riemann hypothesis, right? Are there really, really natural, arithmetical questions that are independent of set theory? So this is not quite the same question, but this is a, sort of a more precise, this is a question that has some precise answer, and I would like to know it. Okay, so now I can tell you what my student Adam Yedidia did for his master's project, which is that, so he built on work of the famous logician Harvey Friedman, who's one of the only people to have thought about this question. And, and Friedman found sort of, arithmetical statements that are sort of more natural than, ZF is consistent, although still very, very wildly unnatural, but which are provably independent of set theory. Okay, and so Adam used Friedman's statement as the starting point, and so as a first step, he's constructed a one-tape, two-symbol Turing machine with about 380,000 states, whose behavior is provably independent of set theory, of ZF, set theory specifically.
If it terminates, then there is a finite proof clearly in set theory, right?
Yes. Okay. I'm assuming set theory is consistent. I'm sorry.
No, but if the machine does terminate.
If the machine terminates, then set theory is inconsistent.
I see.
So that's the first question we ever want to ask an oracle, right?
I don't know. I mean, I'm pretty confident in the answer to that one already. If I get one question to an oracle, I think I'd ask something that I was more uncertain about. But, it's like people say, well, would you ask a genie whether P equals NP? It's like, no. If I were a physicist, I would just say it's a law of nature that they're not equal. I know the answer, so I don't know how to prove it. Okay, so then he also found a machine with about 8,000 states that halts if and only if there's a counterexample to Goldbach's conjecture. One with 30,000 states that halts if and only if there's a counterexample to the Riemann hypothesis. There's a lot of engineering that goes into this, sort of to design a special purpose programming language, which then gets compiled down to multi-tape Turing machine, which then down to one-tape Turing machine. And, in ongoing work, we have an improvement to this. So this was all based on sort of taking this, of course you need to, in practice, you have to write it in some higher level language, right? But then we were just compiling that language down to Turing machine. That produces a huge blow up in the number of states, right? Now what you can do instead is write an inline interpreter, which itself is a Turing machine, right? Where the first thing the Turing machine will do is it will just write, the higher level program onto the tape, and then it will, just run that program, right? And that gives you an order of magnitude savings in the number of states. And so we expect that we'll get down to a 40,000 state machine for ZF set theory, and 12,000 for the Riemann hypothesis. Okay, so the conclusion is, that presumably humans will never know busy beaver of 40,000. And so I ask the question, what about busy beaver of 6, busy beaver of 10? There's still, several orders of magnitude gap between the upper and lower bounds. It's a fun question. Okay, so the final thing I wanted to say a little about for a few minutes is post lattice. So what post lattice is it's all possible sets of Boolean functions that are closed under composing them into circuits. And So for example, you could have if you have the NAND gate, or if you have the AND or and NOT gates, then those let you express any Boolean function, right? If you have only the AND and OR gates, but no NOT gates, then those let you express any monotone Boolean function. Okay, if you have only the exclusive OR and the NOT gate, then those let you express any affine Boolean function. Okay, and and then you could have only AND, only NOT, only OR you could have only the identity function, right? So and these turn out, if we assume that the constant functions 0 and 1 are available for free, then these turn out to be the only possibilities. Okay, it's these 7. Okay, now one of the so Emil Post, he's the guy who sort of discovered Gödel's and Turing's results before Gödel and Turing, but he didn't publish them. It's a true story. You can look it up. He was a math teacher in New York. Did all this in the 1920s. But one of the other things that he did is that he worked out this lattice of the closed classes of Boolean functions. And he even did it not assuming that the constants are available for free, in which case it is way more complicated than this. And in fact, it's an infinite lattice in that case. Okay, so a question that we asked recently is what is the analog of post lattice for classical reversible gates, meaning permutations of the set of k-bit strings for some k. Okay, so the ground. Let me say what the ground rules are. Okay, so swapping bits is free, right? You have a set of bits. You can permute them however you like. Okay, and you're also allowed to have as many ancilla bits as you like. So you can have lots of extra bits that are, say, initialized to 0 or to 1. But the key rule is that the ancilla bits have to be returned by the end of your computation to whatever their initial states were. Okay, because if they're not, then the computation was not really reversible. Okay? So let me give you a few examples of classical reversible gates. Okay, we know these well in quantum computing, but you can also just consider these as classical gates. These were invented in the early 1980s. Okay, so there's the controlled NOT or C0 gate, which takes 2 bits and which flips the second bit if and only if the first bit is 1. Okay, now this gate is not computationally universal because it can't do it can't implement AND, for example, right? It can only do affine functions. Okay, then we've got.
Is it the XOR?
What?
This is the XOR, right?
Yeah, that's right. It can do XORs. Yeah, but by affine I mean affine over the field of 2 elements.
No, I'm just surprised you call it C0 and not XOR because it seems to be XOR.
So like this bit gets knotted, if and only if this bit is 1.
But both come as output, I see.
Yeah, both come as output.
Yeah,
that's
okay.
right.
Yeah.
No bits can get destroyed.
Yeah.
That's what reversible computing is all about. Okay, good. Okay, so then the Toffoli gate is also called the controlled NOT or CC NOT gate. Okay, this takes 3 bits and it flips the third bit if and only if the first 2 bits are both 1. Okay, and now this gate is already universal. Okay, this is a universal gate, both in the sense that you can compute any Boolean function with it, because it can implement AND and NOT. Okay, also in the sense that you can do you can implement any permutation on the set of n-bit strings by an array of Toffoli gates and with just 1 ancilla bit. Okay, that's a theorem. I'll show you how to do it with lots of ancilla bits in a later slide. Okay, and then an interesting case is the Fredkin gate. This is another 3-bit gate where if you swap the second and third bit if and only if the first bit is 1. Okay, so this gate is also capable of universal computation. Okay, but this one cannot do any transformation on the set of n-bit strings. Why not? Well, for one thing, this gate is never going to change the Hamming weight of your string. right? It will never change the total number of 1 bits. Okay, so it's as if, the Fredkin law of physics satisfies the conservation of energy, something where energy means number of 1 bits, okay? And that's something that can just never be violated, okay? So we have 3 different reversible gates, 3 different behaviors, and so then the question we ask is, well, what are all the possible behaviors, okay? And, when is your, under what conditions will your gate be universal, like the Toffoli gate? And there's been an enormous amount of work on reversible computing, and yet no one had asked that question, even though it has such a simple answer. Okay, so this lattice diagram here basically is the answer to the question, which we have a 66-page paper that we just put out this year, which gives a complete classification of every possible set of reversible gates in terms of which reversible transformations they generate. And so you got at the top, is the Toffoli class, here's the controlled knot class, here's the Fredkin class, and above Fredkin you can have gates that only have to preserve the Hamming weight mod k for any k of your choice, right? So that gives you an infinite set of classes. Okay, and then all of these here are affine classes, but they could be affine while also conserving the Hamming weight mod 2. Okay, or they could be affine while also conserving the Hamming weight mod 4. Okay, those are the only 2 possibilities, by the way. Mod 2 and mod 4 are special here. Okay, and and there's some other things like conserving inner products mod 2. So this is probably the most complicated theorem I've ever been involved in proving. Okay, so it's not hard to see, just to give one example, why the Toffoli gate generates all reversible transformations if you're allowed to have a whole bunch of ancilla bits, right? And the basic idea is that if I have some reversible transformation f that I'd like to implement, I can certainly compute f, with the use of a lot of garbage, right? So I can generate a lot of waste products along the way that record the intermediate steps in my computation. Then the whole problem reduces to how do I get rid of those waste products, right? And so then there's a whole rigmarole for doing this. I can take f of x and I can copy it into additional ancilla bits, and then I can do what's called uncomputing, which means running my entire circuit of Toffoli gates backwards. Okay, which takes this whole thing and maps it back to x. Then I have x and f of x. And now the problem is just how do I get rid of x? Okay, well, because f was reversible, I can then use f of x to compute x, right, like that. And then I can take x and I can controlled knot it into this register, which gets rid of this x over here. And then I just have this. And then if I run this computation backwards or uncompute it, then I'm left with just f of x. Okay, so there are some combinatorial results that I think are very cute, and that sort of are some of the centerpieces of this classification theorem. But I'm not going to go into these because I'm running out of time. So I should say my favorite open problem here is to classify all the possible sets of quantum gates acting on qubits in terms of which unitary transformations they can generate. Okay, in fact, this question was our original motivation. Okay, and this one remains wide open. Okay, even just classifying all the possible 1 and 2 qubit quantum gates, no one has done or seems close to doing.
Some things are known.
Yes, many things are known, yes. We know many sets that are universal. In fact, we know that a Haar random one will be universal with probability 1. We know many, we know certain special ones that are not universal. But to give a full classification seems like a very complicated problem in representation theory and Lie algebras.
So how many non-universal?
That is part of the question.
No, but how many do you know already?
Well, okay, the main ones we know is you can have classical gates, and then you can have what are called destabilizer gates. Okay, which are used in quantum error correction, right here. And you can have the stabilizer gates conjugated by some 1 qubit non-stabilizer gate. Okay, and and then the question is, are those basically the only examples of or you could have 1 qubit gates only, or 1 qubit gates plus swaps, or silly things like that, right? And then the question is sort of, are those the only examples that fail to be universal, or are there others?
But we know
Yeah.
that the Boolean case is just extremely simple. Once you go from a 2-element domain to 3-element domains, and you
Yeah.
ask the same question, then all break
right,
loose.
right.
So
Yeah.
we got spoiled by looking at the post classification to think that these things should have nice countable classification. But it's already, you don't have countable classification for 3-element.
That's true. So yeah. So okay. So I'm not. So notice that on this slide, I'm not asking for a classification of quantum gates acting on Q trits. Okay, acting on three level systems, right? So yeah, of course, you're fighting against an onset of complexity that you can that you can never you can never win in the limit of a large alphabet. Okay, but but usually normally in quantum computing we do talk about qubits.
I know,
right?
but even qubit is really right. The set of values there, right? Because the superposition, it's a large set of possible values in some sense.
Yeah.
So it should behave more like looking at algebra with many elements, rather than 2-element algebra.
Well, no, because there are many quantum states. So a spin 1/2 particle, for example, really is a qubit. It is a superposition of 2 orthogonal states, right? You can have particles of higher spin that are superpositions of more than that, but there are certainly many natural quantum systems that just have 2 orthogonal states, and and of course you can have a whole continuum in between them, but that But so I think answering the question for qubits would be a very natural thing to do. It could be done, but it has not been done. Okay, so here's some of the progress that we've been able to make with my student Adam Boland. We classified all the 2-mode beam splitters in quantum optics. That was already like 15 pages of representation theory. My students Daniel and Luke were able to classify all the possible sets of stabilizer gates. Turns out that there are 57 classes of them. Okay, and the questions are like exactly what Guy was asking. Are there interesting discrete subgroups other than the stabilizer group and its conjugates? Does every non-trivial continuous subgroup, lead to universal quantum computing? Okay. So the discussion questions that I find interesting, what would a universe look like where the Church-Turing thesis was false? You could say that our world, because it's quantum mechanical, seems to falsify the polynomial time Church-Turing thesis, but not the original computability thesis. There are these hypercomputing ideas that, where you can imagine devices that would solve the halting problem, right? But in our world, all of those seem to be precluded by, for example, the Bekenstein bound, okay? By quantum gravity. David Deutsch has very provocatively argued that, in a universe with different laws of physics, the halting problem would be easy and the and function would be hard. Right, he's trying to make the point that all of computation is subordinate to physics, right? And okay, so my question for Deutsch is simply, okay, good, what are those laws? Give me an example. Show me what those laws are, right? Where and is hard and the halting problem is easy. What would an interesting model of computation look like that could solve its own halting problem? What would an interesting set of laws of physics look like that were not capable of universal computation? Okay, so I had a little vignette about a machine that's in the lobby of the Stata Center, which sort of fails to be a universal computer for very, very interesting reasons. It turns out to be, I was able to prove that the problem of simulating this machine is complete for a complexity class called CC, which seems to be a proper subclass of P. It's the class for which the stable marriage problem is complete. Okay, so this machine seems able to, find stable marriages but not solve linear programs, for example. But anyway, I won't go into that because I'm out of time. So my conclusion is that the subject of universality is almost 100 years old, or almost 200 if we go back to Lady Ada. Yet I think there are still basic questions that remain to be answered. So thank you.
So let's stop here
Yeah.
and convene at 1:15 for Q&A.